Now, when you press your hands together, each hand experiences a contact force. So, contact force is when two objects are in contact with each other. As soon as you stop the contact, the force stops. Now, what if you take a compass? Remember, a compass is a magnet uh, floating on a little bit of water. So if you put a compass on a level surface far from any other bar magnets or magnetic fields, then the needle will move and it will stabilize. We already talked about this. We talked about how the magnetic needle will orient itself with the magnetic field of the Earth, because if you don't have a closer magnet that's disrupting its movement, then the Earth's magnetic field is the strongest magnetic field, and it will orient itself that way. Now here we see we see something different. Here we see a bar magnet, and we see a whole bunch of little compasses around that bar magnet. Now in this case, the strongest magnetic force is the magnetic force of that bar magnet, because the distance is very small. So you can see these magnets no longer point north. They orient themselves uh, kind of like the iron filings did. They orient themselves along the magnetic field lines. Compasses can be used to detect and map a magnetic field. They're not just for finding directions around Earth. In this image, we see that the compasses on the right side of the magnet orient themselves with their north poles pointing toward the end of the bar magnet. So that tells us that the right side of the bar magnet is the South Pole. The North Pole of the compasses point toward the South Pole of the magnet. Electric and magnetic fields both use field lines. Remember, we learned about field lines when we were learning about electric fields. The closer the field lines are together, the stronger their force is, and the direction, the arrow of the field line, shows the direction of the force on a in this case, these are electric field lines. Remember, the arrow shows the direction that a positive test charge would move if it was put in that magnetic or in that electric field. The same thing is true for magnets, that we draw an arrow showing which way a test magnet would move if we put it in that field. So, which direction do you draw a magnetic field line? A magnetic field line shows the direction that a north a north monopole would move if you put it in the field. Now, a monopole is a particle or an object that has only one magnetic pole. It's only north. In reality, there's no such thing, or at least no such thing has been discovered, that is a monopole. Unlike unlike electrostatic charges, magnets always occur in north and south together. So there you can't just you can have an electron and it just has a negative charge. You can't have as far as we know so far. They're theoretical, but as far as we know, we can't have a magnetic object that just has a south pole or just has a north pole. So the magnetic field lines show the direction that this hypothetical north magnetic monopole would move if it was put in the field. Just like in an electric field, the field lines show the direction that a positive charge would move if put in that field. So you can kind of associate positive with north, even though don't think they're exactly the same thing, but we treat them the same way when we're drawing these field lines. Here's an illustration of that. We can see these field lines. We can see that the direction of the arrow goes from the North Pole to the South Pole, and the compasses align themselves along those magnetic field lines. We can also see how close together those field lines are. The closer together they are, the more the more or the stronger the magnetic force is. What would happen if you put another magnet right below this magnet that had the same orientation? How would that change the field lines? Well, they would still be in the same direction, but they would probably be, or the same general direction, but they would probably be closer together. So the field lines would show a greater magnetic field strength. Here we see a close up of the videos that we saw, or what was shown in the videos that we saw at the with the pieces of paper on top of the magnets with iron filings. Now we just see it up close. So this can help show you when the north and north poles are pointing toward each other, we see a gap between the two magnets because there's a repulsive force. So the magnetic field lines they start out going toward they basically just go away from the other magnet, and we can see the magnetic field lines doing that. On the right side, we see an attractive force. We have the north and south poles pointing toward each other, and so we can see the magnetic field lines going from one magnet right to the other magnet.